Hello, everybody. So today we're going to talk about the P versus NP problem. We already discussed what is P, polynomial time, the languages that can be decided in polynomial time. And today we're going to define NP towards the goal of discussing the P versus NP problem, which is not only an amazingly important problem in computer science and beyond, but also managed to get its way into popular culture. And here you can see it in Futurama and Simpson already many years ago. So by now it's really a cultural icon. So to define a non-deterministic polynomial time, NP, we will start by reminding ourselves what is non-deterministic Turing machines, and we'll do it with a little bit more detail than when we described it before, because before we didn't, it didn't play such a major role. So these are just like standard Turing machines, except the machine can proceed according to several possible transitions or no transition at all, just like an NFA. The machine accepts an input string if there exists an accepting computation history for the machine on the string. Here is an example of how it would look graphically. So we have this graph and it has transitions on it, on every arrow, and there could be more than one arrow with the same transition. So you can decide which action to take to which state to get, or even if to go right or left. And there could be other states with no transition of a particular kind. So what do we accept here? We will accept the string 0, 0. And although we have a reject path for it, we also have an accept path for it. And we will also accept the string 0. So you can go with 0 here, and then say the empty string and move here. And that's essentially it. For no other string do you have any path, let alone an accepting path. And the empty string, of course, is rejected here. So more formally, a non-deterministic Turing machine is still a 7-tuple with all of these ingredients. Q is a finite set of states. Sigma is the input alphabet, and the empty string, the empty cell is a symbol that is not in the input alphabet. So we can distinguish where the input is and where we have empty cells. Gamma is the tape alphabet that contains both the empty cell and all the input alphabet and anything else that we may want to use. The interesting thing is that the transition function takes a state and a symbol that you read, so which state you are, which symbol you are at, and it gives you a collection of possible transitions, and the collections can be empty or it can be everything. So instead of specifying what state you get into, what alphabet symbol, what tape symbol you're writing, and whether you're going left or right, it can specify many possible transitions. Q0 is still the start state, Q accept is still the accept state, Q reject is the reject state, and these are different. Q reject is different than Q accept. So almost exactly like the definition of a Turing machine, apart from the transition function being more general. Instead of outputting a single transition, it outputs a subset of all possible transitions. So with that, how do we define acceptance for a non-deterministic Turing machine? Let n be a non-deterministic Turing machine, and accepting computation history for n on W is a sequence of configurations, C0, C1, CT. We already saw that, where C0 is the start configuration. So recall the start configuration is just Q and the input W, indicating that the head is in the leftmost position and the state is the start state. Qt is an accepting configuration, which means that first it is a legal configuration and then the state written there is an accept state. And each configuration yields the next. So there is a way to move from configuration CI to configuration CI plus 1. Now, if that's the case, so if there is a history of T configurations, T plus 1 configurations, then we will say that NW accept in time T. And if there is no such history, then it either not accepting or at least not accepting in time T. N is time complexity T of n if for all n, for all inputs of length n, and for all histories, n halts in T of n time. Sorry. Now, we want, right, we are in the world of decidable languages, so we somehow want the non-deterministic Turing machine to halt always. So all histories are going to be short. In fact, you can turn any non-deterministic Turing machine into one that halts after T of n steps by having a clock that tells you to stop after T of n steps. And if there exists some accepting configuration that is shorter than T of n, then we didn't change the language we recognize, but we did manage to halt always. Non-deterministic time T of n is all the languages that are decided by an order of T of n time non-deterministic Turing machine. Time T of n is naturally contained in n time T of n. Why is that? Well, a non-deterministic or a deterministic Turing machine is a special case of a non-deterministic Turing machine. So if there is a deterministic Turing machine that decides in this time, then there is a non-deterministic Turing machine that decides in this time. It's just the same. Is the other more interesting case is a question is time T of n equals time T of non-deterministic time T of n for all T of n. So do we have containment in the other direction? And this, even in this very, very strong fashion, this is not known. We do know something for limited models like single tape, but that's not important, and for very limited amount of time. But beyond very simple edge cases, we just don't know how to handle this question. So we define this non-deterministic Turing machines, and the question is what problems can be efficiently solved non-deterministically, but not deterministically. We don't know it. We know problems that can be solved efficiently non-deterministically, and for those questions, we kind of conjecture that they cannot be done efficiently by deterministic Turing machine. One example is the Clique problem. You have a graph, and I hope you remember what a graph is. It's a collection of nodes and edges between the nodes. And a clique, a K-clique, is a complete subgraph on K nodes. This is a 5 clique. some reason this should be yellow. And you can see that within these 5 vertices, you have all the possible edges. Every 2 vertices here are connected with an edge. This is what a clique means, or a complete graph means. So this is a 5 clique. Of course, in an example as simple as the one we saw, identifying a clique is easy, but imagine a clique on a huge graph like the one here. So find a clique of 1 million nodes within a much larger graph with huge number of nodes. And now, if you assume any of the reasonable encoding of graphs, and there are 2 that are the most popular, adjacency metrics or adjacency lists. Let's think about adjacency metrics. So this is a metric that has all the nodes on one side, all the nodes on the other side, and the 0, 1 for node U and V, where it's 0 if there is no edge between U and V, and 1 if there is an edge. So for any kind of reasonable encoding of a graph, we can define a clique, which is the language of pairs, G, which is a graph, and K, which is an integer, such that G is an undirected graph with a K clique. We also have a version for directed graphs, but here let's discuss just undirected graphs. And we want to show that clique is in non-deterministic time and to the C for some C larger than 1. So non-deterministic machines can decide cliques in polynomial time. So what would this machine do? N on input G, which is a pair of VE. V is the vertices, E are the edges, and K non-deterministically guesses a subset S of V with K nodes. So the size of S is K. So it guesses the clique, and then it verifies it. For all U and V in this S, which we guess to be a clique, we check if U, V is an edge in E. Otherwise, we reject. And if all of those are edges, then we accept, because we just enumerated and found a clique. So we guess the clique and then enumerate all the edges or the supposed edges within this clique and verify that they are indeed there. This is an example where a problem that we don't know how to solve directly, we can verify a solution, and a non-deterministic Turing machine indeed is able to guess for us. Let's give another example, Hamiltonian path problem. Again, you have a graph. This time, let's think about a directed graph. A Hamiltonian path traverses through each node exactly once. So do we have a path here? Yes, this is a Hamiltonian path. It starts at H. It goes all the way to C, and in between it visited all edges. We can also talk about a Hamiltonian cycle. In that case, we would also need here the edge between C and H in the right direction. But this is a Hamiltonian path. Hamiltonian path, more formally, is over, or all the triples GST, where G is a directed graph with a Hamiltonian path from S to T. So the question is there an Hamiltonian path between S and T in G? Hamiltonian path is also decidable in non-deterministic polynomial time. And what we'll do here is very surprisingly, or non-surprisingly, almost exactly the same. Non-deterministically, you guess the path, which is just a sequence of node, V1 up to Vn. And now you verify that this path is a Hamiltonian path between S and T. So you check that V1 is S, Vn is T. You check that all of the vertices are different and that you have enough vertices, meaning that this is a sequence of all the vertices. And now you check that every adjacent pair of vertices is indeed an edge, a directed edge. So vi plus 1 is an edge. So if any of these conditions doesn't hold, you're going to reject. Otherwise, you accept. So you reject if two of these vertices are the same, and then if there is two adjacent vertices that are not an edge, and if V1 is different than S, or Vn is different than T. And otherwise, if all of this hold, then you accept. So this kind of gives rise to this notion of NP, which is an analog to P for non-deterministic computation. So non-deterministic polynomial time, everything that can be decided by in n time n to the k for some constant k. And just like P, it is a robust notion of efficiency as far as non-deterministic time is concerned. Let's try to see NP in a slightly different light, which is perhaps a more useful one. So here is a theorem. L is in NP. If there is a constant k and a polynomial time Turing machine V for verifier, such that the language L can be presented as follows. It equals all the x's such that there exists some y, some string y, with this string y being not too long, at most the size of x to the k, and this verifier on input x and y accepts. So let's prove it. Maybe a little bit reminiscent about the way we kind of looked into recognizability with respect to these computable relations. Okay, proof. If L has this form, then we want to say that L is in NP. And if L is in NP, we want to say that it has this form for some verifier V. So if L has this form, then we can easily define a non-deterministic Turing machine N that is going to decide L in time, essentially N to the K. In time which is polynomial. So you're going to guess y of length at most x to the k. This part is of length of time at most n to the k. And now you run the verifier on x and this y and output its answer. So the running time is, since V is a polynomial time Turing machine that has a polynomially long input, x and y, then the entire run is polynomial time. This is a polynomial time non-deterministic Turing machine. And we want to claim that it does decide L. And indeed, for every x that you accept because there is some y of the right length on which Vxy accepts. So you only accept strings that are indeed in L. And every string that is in L, you could accept, because as long as you kind of guess Y, you can verify by running v of x of Y that it is in L. So you just need to guess the right Y. So indeed, there is an accepting computation. Now we want to prove the other side, namely that if L is in NP, then we can present L in this way for some V, and the main task is to define V. So suppose N is a polynomial time non-deterministic Turing machine that decides L, then we can define V such that it takes two inputs, X and Y, and it accepts if and only if Y encodes an accepting computation history of N on X. We need to show first that V runs in polynomial time. This is easy. Verifying that a computation path is an accept path is easy. You need to check that the first configuration is the initial configuration, the last is an accepting configuration, and between any two, one yields the other. So that's one thing we need to show, that V is polynomial time. And then we need to show that for every X, there is Y of some polynomially bounded length, X to the K, for which V of xy will accept. And indeed, for every X in L, there is an accepting computation path in N. And furthermore, this, because N is a polynomial time non-deterministic Turing machine, then this accepting path is going to be polynomially bounded. And with this, we kind of end. In fact, the examples we saw were pretty much of this form. We saw example with the cliques and with the Hamiltonian path, where Y was either a clique or the path itself, and then V verified that this is a legitimate clique within the graph, or an Hamiltonian path within this graph. So language L is in NP if and only if there are polynomial length proofs for membership in L that can be decided efficiently. So these are proofs that are polynomially long and can be verified efficiently. The proof itself is Y, and the verification is V. And these are known as proofs or certificates or witnesses. So a proof that X is in the language, Y is a proof that X is in the language, or a certificate that X is in the language, or a witness that X is in the language. So for clique, GK is that there exists a subset of nodes S such that S is a K clique in G. Hamiltonian path, GST, such that there exists an Hamiltonian path in graph G from node S to node T. In both cases, it's about an existence of a proof, which is the subset or the Hamiltonian path, and this proof can be verified. So let's give now some more examples. One that will be important for us very soon, when we'll try to show that some problems are particularly hard within NP, is Boolean formula satisfiability, or in short, SAT for satisfiability. So a Boolean formula has these variables, x, y, z. They have logical operations like the negation and or. And they have parentheses to determine order of computation. Otherwise, the order apart from The parenthesis is that negation precedes and which precedes or. So this is a formula, and it has its variables. By the way, a negation of a variable is, or a variable is sometimes known as a literal. So a satisfying assignment for this formula is a setting of the variables that makes the formula true. X equals 1, y equals 1, and z equals 1 is a satisfying assignment for this formula phi. Why is it true? Well, z is 1 means that that's already true, and then the or means that this or this is true. So this, by the way, is not true because not x is false. X is 1, not x is 0. Therefore, this is all 0, but it's or with a 1. Right, and in fact, every assignment with z equals 1 is satisfying. How about this formula? What is it? What would satisfy that? For example, this. So 0, 0 means that x or y is x or y is 0. The whole thing is 0, but the negation of it is 1. And this part, which we need also to show, is 1. So z is 1, and not x is also 1. This kind of trick, when you have a variable and its negation, will actually help us later on in one of the future videos. A Boolean formula is satisfiable if there is a true-false setting of the variables that makes the formula true. So if it does have a satisfying assignment. Is this satisfiable? Yes. You just, you have all independent literals, and you can just make each one of them individually 1. Is this satisfiable? Let's see if this, for this to be satisfiable, this has to be true. If this is true, then this is also true, but then its negation is false. So false and true is false. So no, the answer here is no. Sat is the language of all Boolean formulas that are satisfiable. A particularly convenient form of satisfiability is 3 CNF formulas that have the form a clause and another one and another one. And these clauses, each one of them is the or of 3 literals. So 3 either variables or their negations. So this is 3 CNF formula. It asks for this clause to be true and this clause and this clause. And each one of these clauses asks for one of the literals to be true. So you need one true literal within each one of these clauses to satisfy this 3 CNF formula. Right, so if literals, these are the literals, variables and their negations, and these are the clauses. 3SAT is all the formulas phi, such that phi is a satisfiable 3 CNF formula, a subset of SAT. Theorem 3SAT is in NP. We can express 3SAT exactly in the way we like to express problems in NP. 3SAT is formula phi, such that phi is in 3 CNF, so it has the right structure, and there exists a string y that encodes a satisfying assignment to phi. So Y is the witness, that the satisfying assignment is the witness that X, or that this formula is satisfiable. Perhaps it's not easy to come up with this Y, but once you see this Y, it's very easy to verify. You verify that phi has the right form, and then you verify that each one of the clauses is satisfied by looking at Y. The number of variables of phi is at most the length of phi. So this means that the witnesses themselves are polynomially bounded, in fact, linearly bounded. The second part is to check that the verification can be done in polynomial time. So specifically, if we look at this language, 3-sat check or verify, which are all pairs of formula and Y, where phi is a 3CNF and Y is a satisfying assignment, that this is in P. Namely that you can, in polynomial time, verify given a formula that it is 3CNF, and then that Y that is also supplied in the input is a satisfying assignment. Similarly, we could have just argued that SAT is in NP, because then we'll just check that phi is a formula, not necessarily a VCNF, and then that Y satisfies it. So NP is the problems with the property that once you have a solution, it is easy to verify the solution. When phi is in SAT, or GK is in Clique, or GST is in Hamiltonian path, we can prove with a short proof that this is indeed true, and this can be checked efficiently. So we have a short proof that phi is in SAT is a satisfying assignment, a short proof that GK is in Clique is the Clique, a short proof of GST is in Hamiltonian path is the path. These are short proofs that can be verified efficiently, verified in polynomial time. This is a question to think about, and we will revisit in later videos. What if phi is not in SAT, or GK not in Clique, or GST not in Hamiltonian path? Is there a short proof of that? Is there a short proof of any other form that this is correct? So we will discuss it when we'll discuss CoNP, and later in a very surprising manner when we will discuss interactive proofs later on. So let's kind of return to what we wanted to draw the analogy, and this is between P, the problems that can be efficiently solved, and NP, the problems that once you see a possible solution, you can efficiently verify it. So the question is P equals NP is, can problem solving be automated? So once I know, if I have a problem in front of me, then perhaps I cannot even verify with an answer if it's correct or not. This already makes this problem quite problematic, because how would I be convinced even? So if you don't have a proof, then it's a little bit problematic. Actually, there are, and we'll encounter interesting problems that don't have a short proof, that are not in NP. But this is a huge class of languages of everything that can be verified automatically. And now the question is, can we now come up with a proof? So is the fact that I can verify that a clique is clique, or verify that an assignment is satisfying, means that I can also find such a clique or find such an assignment? This is at the heart of P versus NP. It has been acknowledged the beginning of the century as one of the millennium problems. It carries a nice prize, but in fact, I think that this $1 million prize is actually just the tip of the iceberg for anybody that would solve it. And why do we care so much? We care because this possibility that P equals NP is quite amazing. It means that mathematicians may be out of a job because mathematicians are looking for simple proofs. And if once a simple proof exists, we can just find it automatically, then why do you need a mathematician? Cryptography, on the other hand, as we know, it will be impossible because the cryptography that we have now relies on secrets, relies on things that where you can verify a solution. So if I see an encryption, I can see that it is encryption of the message M if somebody supplies me with the randomness that was used to create this encryption. So we can think about finding the message as finding a proof. And then we can just find it. So there will be no encryptions of this sort. In some sense, every aspect of life could be efficiently and globally optimized. Everything that we can kind of acknowledge and appreciate a good solution, we can actually find it. So fortunately for somebody who's a mathematician, we conjecture that P is different than NP. Finding that would also tell us a lot about computation, will tell us we are so far from it, from being able to prove it. Once we'll prove it, we'll be able to say a lot. But I want to say that this would not necessarily save mathematicians, because mathematicians themselves, if P equals NP, then in fact, we can do much better than what mathematicians can do now. We can find all short proofs if they exist. Mathematicians find a lot of proofs, but it's not necessarily that we can find all of the proofs. It takes us years, and sometimes we find, sometimes we don't find. And so to replace mathematicians, the bar is actually a bit lower. We just want programs that could do as well as humans in finding these proofs. And that I actually suspect could happen, but now, not fortunately for all mathematicians, but fortunately for mathematicians my age, I think we have enough time to retire before this happens. Some parting thoughts. We have discussed this notion of what can be done in polynomial time. One is verifying, which means that you verify that a solution is legit once you see it. And the other one is deciding if a solution exists, if you don't see it. This is extremely fundamental. It will say a lot of things, and we will see some examples later in the course, whether it is true or false. If verifying equals deciding P equals NP, then dramatic consequences will happen. But P is different than NP would give us, proving that would give us, for example, some hope to basing cryptography on foundations that cannot be shaken. So have a cryptography that cannot be broken. Thank you.